Thanks you all for joining. In this session, we are going to talk about cloud native app development using Spring and YugabyteDB. Bit about myself. My name is Nikhil Chandrappa. I'm a software engineer at Yugabyte. I work for the ecosystem engineering here. We work on integrating Yugabyte with all the modern development tools like Spring Framework, GraphQL, YugabyteDB drivers. Prior to that, I was at Pivotal. I was like a senior data engineer there, working with Fortune 500 companies for building cloud native APIs, cloud native data APIs, and data pipelines at Pivotal. So before we get started, just wanted to go over the agenda, what we're going to talk today. We're going to talk about the cloud native app development using Spring, obviously. And in order to explain the concepts much better, we are going to talk about a real world example, which is going to be deployed using Kubernetes. It is going to be deployed on Kubernetes, and we are going to use Istio for traffic management. So we're going to explain the architecture of our app and also do a bunch of code walkthrough, like walk through how we are using Spring annotation and things like that. And we're going to talk about the driver support we have for Yugabyte, the both blocking and non-blocking drivers, and also how everything works with the Spring data, the Spring data, right? At the end, we're going to finish off this presentation with another demo where we're going to scale the relational SQL backend without needing a load balancer using one of our cluster-aware JDBC drivers. So over the last decade, there has been a significant change, right? How we deploy, how we develop and deploy software. So it used to take a software development cycle from like 6 months altogether. Now it's like within few days or within few hours, you can put code into production. In order to make that happen, people started moving from, and in that kind of modern microservices architecture, it is very essential for you to have like high resiliency and fault tolerance. That's why people started moving their applications from just deploying on a one data center or for two data centers for HA perspective or fault tolerance perspective. It's went to deploying on multi-regions and multi-clouds also. Like you deploy apps on your data center, on public clouds and things like that. And we moved from using like beefier VMs or bare metal machines to breaking down those applications so that it can be deployed into containers and all the into a stateless applications so that it can be managed in a platform. And also we moved away from deploying large J2E applications in smaller microservices or domain-specific microservices. And Spring has been in the forefront of this cloud native journey. If you see, these are like some of like very popular internet-based companies, right? Like Netflix of the world, Doctors of the world. The one thing common between all these companies is they are like huge Spring users and they have built their business on Spring backend and microservices. Of all these companies, one thing that comes to mind is Netflix. Netflix was it was one of the pioneers of cloud native journey, right? They were one of the first companies who broke down their monoliths to microservices, and because of that, they came up with a bunch of open source projects on the cloud native front, which supports 12-factor apps like service discovery, config server, Hystrix, and things like that. So Spring framework kind of took up all these best practices of cloud native cloud native app development and came up with a Spring Boot project, which kind of reduces the amount of boilerplate and the dependency know-how that the app developer needs to have. That's why Spring is becoming one of the leading frameworks in enterprise Java development. And also back in 2018, Netflix kind of announced that they are moving and they are embracing Spring framework in their entire app development. And also since all the open source projects they had, Spring has kind of taken over, they have access to a wider audience, a wider community to build all the cloud native features. So there's a really good blog that Netflix has published and why they moved to Spring framework. You can go and read about that article. It's a really good one. If you see, the Spring has a portfolio of products that it supports. Like it has projects which help you build microservices faster, to reactive, to serverless, and even event-driven and batch processing. That's why Spring Framework kind of has become a de facto for modern application development. So now let's take a stock on and see why do we need, or why there is a need for modern cloud native distributed SQL, right? So don't get me wrong, like all the Postgres and Oracles of the world have done a great job in supporting the modern microservices architecture till now. However, there is a need for modernizing backends, because some of the things for scaling and high availability are kind of bolted on for the traditional databases. We need to have a database which is built ground up and designed ground up to scale linearly, and also supports smart drivers, like which are topology aware, data aware, so that you can do a millisecond, you can get millisecond response time, you can do like single hop fetch and things like that. And also the databases needs to start supporting reactive streams. So reactive streams is the next push from the Spring team, and also all the app developers are using Reactive. Reactive has been prevalent in the UI, UX for a long time, but now it is coming for the backend and middleware development also. So you need to have your database which provides reactive-based non-blocking APIs for fetching data. Apart from that, you need to be able to provide developers a self-service way of provisioning your databases, so that they can quickly spin up a development server and start prototyping their apps. So all those things, for all these reasons, we kind of need a modern cloud native app, a cloud native database. So for those who don't know what distributed SQL is, distributed SQL aims to provide a highly scalable relational database system, so that you can scale your application requests to thousands of transactions per second. At the same time, it gives geo-distribution, so that it inherently provides fault tolerance and a high availability of the data. Even if your a cluster of servers in Americas go down, if you have replicated data in other geographical location, it stays alive, and your apps can go start working with those instances. So that's why at the core of a distributed SQL databases, you have high availability and fault tolerance built in. So Yugabyte is one such database. It's one of the leading providers of a distributed SQL. It has it provides low sub-millisecond latency for reads and writes. It's cloud native, which means you can deploy on the modern cloud platforms like Kubernetes, Cloud Foundry, and it's open source. It's 100% open source. Everything is Apache 2.0. And that's one of the big decisions they did back in 2018, where they open sourced the entire project to Apache Foundation. These are the few terminologies we need to know as app developers when we start working with YugabyteDB. So Yugabyte kind of follows a layered approach. It kind of provides it provides multiple APIs in a layered fashion. Right now, we have support for SQL-based, relational SQL-based API, as well as a NoSQL-based API, which we call it YSQL. And all these APIs kind of built on top of a DocDB engine that we have optimized using RocksDB. So all the database, all the data storage, as well as distribution of the data, like sharding of the data, is taken care by the DocDB layer. On the top layer, we kind of maintain a wire compatibility with Postgres and Cassandra APIs. If you have, if you need to know like in depth of how our DocDB store works, there is like a bunch of material out there in Yugabyte blog, and there's also different videos, and you can go ahead and take a look. In this presentation, I'm not go into go in deep on the DocDB layer itself. So just keep it more on the YSQL and the YSQL part of YugabyteDB. In order to like piece all these things together, right, we wanted to come up with a real world application. Like we wanted to like have a reference application which kind of built on top of the cloud native architecture using microservices, and also it can use a cloud native database deployed on a cloud native platform, right? There's like a lot of cloud natives here. So I'll quickly walk you guys through the application that I'm talking about called Yugastore. It is nothing but an e-commerce application, which is similar to your Amazons or Targets or Walmarts of the world. And also it's like more prevalent for us that we are talking now, where scalability of all these applications is very much important, since all of us are working from home and doing online based buying of all the materials, right? So this is our marketplace app, which is like an e-commerce app. What we have like thousands of products, and we have not loaded the entire data set. It has like, we have millions of products that we have simulated, and we have like bunch of different categories where each of these products are. So similar to any other e-commerce application, I can go ahead and say add the let's just say I go and add it to cart. It gets added to cart. I can go and check out the cart, and the checkout happens, right? So this is like a simple application that you are seeing, right? Like what we want to look into is like how all these APIs are built behind the scene, how we have broken down the APIs into its own domain models so that it can be served by its own microservice. So let me go back to my presentation. To quickly talk about how what cloud native stack we are using. So the microservices itself are developed using Spring and Spring Cloud. And the UI piece that you just saw, it is based on React and React Native. And the entire apps are the swarm of microservices that we have implemented, have been deployed on Kubernetes, and also within Kubernetes, we have Istio doing the traffic management for all these microservices. So we are gonna not talk much about like the Spring Cloud aspect of this app. We are gonna talk more about how we have developed the access pattern or the data access layer of these microservices. So on a high level, this is the architecture we have for this microservice, for this application. So we have if you see, we have like three main microservices. Each of them is serving its own table or its own data from Yugabyte cluster. So the product microservice is responsible for serving the data for this page, this particular page, where if I click on a particular product, it can go and fetch the data from the product's metadata table. So we are currently in order to design the access pattern for this particular domain, we are doing a directed fetch. We are fetching the data based on the product ID. That's why we want to have a key value based access. That's why we went with the SQL of Yugabyte, which supports NoSQL way of accessing data, right? We can do a directed key fetch. That's why our product microservice is using the SQL API. And the other microservice that I wanted to quickly touch upon was the cart microservice. So in our cart microservice, we want to maintain consistent transactions, and we want to have a highly consistent cart so that we can keep the inventory in check and things like that. So that's why we are using CQL, which is PostgreSQL. We are using SQL here, it is the YSQL of YugabyteDB, which is Postgres wire compatible. So all the Postgres transaction semantics will hold good here. That's why we went ahead and used SQL for cart microservice. And if you dissect what each microservice is made of, like in our microservices, we are using, since we are deploying on Kubernetes, we are using Spring Cloud Kubernetes and Netflix's Ribbon client for doing the service discovery of each of those microservices. And we are using Spring Data for accessing the data from the YugabyteDB layer, which kind of provides the repositories and the Spring Data REST, which like kind of abstracts away all the boilerplate code. For the developer, all we need to know is a bunch of annotations, and we can quickly start prototyping an app using Spring. And behind the scene, we are using YugabyteDB, as I said. the Yugabyte itself supports distributed asset transactions, and also the other thing that we're going to talk about later in the presentation is the cluster-aware JDBC data source that Yugabyte provides. It's kind of bringing in the NoSQL world to the SQL JDBC drivers. In order to let me quickly, before I go on to Istio, I just wanted to quickly show the setup that I have on Kubernetes. So let me bring down one other application. Okay, domain console. So this is the Yugabyte's platform. So this is where an app developer can log in and create different Yugabyte databases. So we call it as a Yugaware platform. So in Yugaware, a universe is called as a single universe is nothing but a single database cluster. So I already have a cluster created as part of for this particular app. However, I can quickly go ahead and show you what it takes to create a new YugabyteDB cluster. So all we have to do is, like say, I'll call it as a demo cluster, provide a bunch of things. I already have a GKE cluster where this is going to be running, and I have configured the GKE kubeconfig in my Yugaware so that it knows it has the credentials and knows where to deploy the cluster. And next thing is specify the region where you want to deploy the cluster, and number of pods kind of specifies the number of data nodes within the cluster. So I'll go and create an extra small cluster. By default, we are not enabling YSQL. You can go ahead and enable YSQL, and you just click on create. It's gonna go and create the database for you. So this is like within few steps for an app developer, he can quickly start a cluster and start working against it. Going back to our Yugastore cluster. So if you see, I have like a bunch of tables here. I have one YSQL table, which is the SQL table, and the other is a SQL table, which is the NoSQL way of accessing the data. So each of them, you can, if you click on each of them, you can go and see a bunch of metrics of how they are behaving and things like that. So Yugabyte kind of provides all the details for us. And the next thing I wanted to show was the apps that we have deployed, the microservices we have deployed in our Kubernetes cluster. So I'll just go and do Kubernetes get pods. I'll come back to like configuring and deployment of these microservices, just to showcase like how we have broken down these apps into smaller microservices. You could see one of the advantages of using microservices is you can deploy the multiple different versions of microservices, and also like with use of Istio and traffic management, you can kind of direct which microservice takes more traffic. Like if you are doing the A/B testing or like a canary testing, you can figure out all those things. So that's about the deployment of our microservices. I can quickly show you my YAML that we have used for deploying these microservices. So one interesting thing that we want to look into is like the URL that we are providing for connecting to our database. So if you see the YugabyteDB cluster from the Spring Microservices app, it can go ahead and connect to the cluster using the Kubernetes native services. We don't have to expose any load balancers or anything, any other things. Using just the Kubernetes a native primitive, a native service instance, we can have our apps to connect our databases. It is like you can have all your APIs sitting in the same place where your database is, so that you can have faster, faster response times, very low latency response times, and things like that. Any questions on the app so far? I'm going to show you the actual code next. Before that, I just wanted to see if there is any questions. Oh, okay, I see there is a question. Is Spring Boot essentially the same as Spring support offered by JBoss from Red Hat or the open source Wi-Fi project? So Spring Boot is a project that provides. It's not a. It is not a Spring support per se. Spring Boot its own in itself is a separate Spring top level project. What it actually does is Spring Boot kind of simplifies the way you bring down dependencies. So you kind of bring down the Spring parent form, and after that you don't have to maintain any dependencies of your subsequent jars. Like say if you're using Spring Web, Spring REST, Spring JPA, you don't have to mention the jar version of those dependencies. You just have to mention the top level Spring Boot parent version. The Spring Boot knows which are the compatible versions for that particular parent and brings down those versions. So like previously it was like one of the most painful things, right, to get the Spring dependencies right. In order to alleviate that pain, Spring team came up with Spring Boot project. Apart from that, it has a bunch of other things like intelligence of knowing where that Spring Boot app is running. Like say if it is running on a Kubernetes, it knows how to parse the environment variables and bootstrap like a database data source or like a message broker, things like that. So that is what Spring Boot is. So Spring Boot is just a top level Spring project. And I think I was not sure that whether Red Hat has support for or Spring or not. I mean, yeah, Red Hat has Wildfly and VMware Pivotal has Spring Boot. So that's the comparison there, if I can think of one. Cool. Hopefully that answers your question, Rob. Okay, perfect. Quick second. Let me go back to my deck. And in order to deploy the Kubernetes cluster, right? In order to deploy the Yugastore microservices, right? We have gone with Kubernetes and Istio because that's where the industry is going towards. And you can see a lot of companies are coming up with the Kubernetes story, or there's like a lot of development vendors are coming up with different products for Kubernetes, whether it is it's on the networking side, security, databases, application development platforms. Everybody are moving towards Kubernetes. So even in cloud or the microservices journey, there has been kind of people have evolved from how they were using microservices and how they are using microservices in Kubernetes. Before, as I said, Netflix kind of came out like cloud native design patterns and a bunch of open source projects, right? Like Netflix Eureka and things like that. Those used to be its own app or a jar that you had to have running in your platform. Now with Kubernetes, all those things are taken away where you can seamlessly start working with the discovery service that is native to Kubernetes using its Kubernetes services. And all the clients like the Rebel client, which is like a load balancing client-side load balancer that Netflix provides, all those things can automatically work with Kubernetes to figure out where your microservices runs. And also, in addition to that, what Istio brings to the table is Istio kind of provides you capability of traffic management, whether if you're doing A/B testing, or if you're doing canary testing, or just fault tolerance testing, right? If you're doing any chaos testing, Istio provides like a lot of capabilities for doing traffic management using just YAML deployments. And also it provides observability and security at a single place so that you don't have to embed everything into a microservice. So Istio takes care of embedding a proxy and taking care of and the traffic between the entire microservices. In our setup, what we have currently using is we are currently using Istio's Ingress gateway. So Istio's Ingress gateway provides kind of a load balancer, which is centralized load balancer for a Kubernetes environment, where any outward facing or a public facing API, you can have an Ingress gateway so that you can kind of expose, you can kind of maintain all the Ingress rules and the load balancer rules at a single place, and it's not scattered around everywhere. So if you see here, my React app, the React app currently I'm using endpoint. This endpoint is nothing but Istio's Ingress load balancer endpoint. So this particular app doesn't have its own load balancer. So one of the complaints that we used to have in Kubernetes environment is on that sense, where you need to have like a lot of load balancers in order to expose APIs. So Istio kind of solves those kind of problems where it brings in Ingress gateway. If you see, this is very straightforward how we are deploying this Ingress gateway. All I'm saying is this Ingress gateway is targeted towards one of our microservice, which is the retail app UI, and all the path after the / prefix, it has to go through this Ingress gateway. So none of the, if there is, you can use it for maintaining security and DDoS kind of attacks. You can prevent a bunch of things like that. Cool. So now comes the actual crux of this presentation, where we are going to talk about how Yugabyte fits in to this microservices architecture, how Spring Data, how Yugabyte works with Spring Data ecosystem. So if you know Spring, if you're a Spring developer, I think you might have used Spring Data JPA or one of these other Spring Data projects. So Spring Data kind of provides like a Spring Data kind of provides like an abstraction for all the databases, right? Like a unified way of accessing a database, whether it's a relational database or a non-relational database. It provides a bunch of APIs which are common across all these products. So if you see Spring Data is loved by developers. If you go and see the Spring Data Git repo, it probably has more than 50,000 GitHub stars, and those many enterprise application developers use Spring Data. So there's like two main components, or the two main capabilities that Spring Data provides. One is to dealing with the boilerplate code involved in configuring any Spring Boot app or any Java application per se. So you just have to bring down a right dependency for a database, and the Spring Boot auto reconfiguration kind of takes care of figuring out what the database actually is. And based on the application properties, it figures out where the credentials are and automatically creates a data source for you. You don't have to write like a bunch of code just to bootstrap your data source. So Spring takes care for you, or Spring Data takes care for you. Another important thing that it provides is a repository support. So repository support is nothing but boilerplate code implementation for all the CRUD operations, like a common CRUD operation. Let's say whether you're inserting data, updating data, or deleting data. So all those things are already pre-built or pre-implemented by Spring. So that's why with just few annotations, you can quickly start prototyping a Spring Boot app working against any database. And what we have done within Yugabyte is we have taken effort to implementing integrations for all these Spring Data projects. So since we have a bunch of distributed SQL features that are new to the SQL world, like cluster awareness in a JDBC driver, and also being able to bring in the intelligence of where the actually app is running, like how to read the application properties or the config maps from Kubernetes. We have built all those things in our drivers. So that's why we have brought in the cloud native aspects of to our JDBC drivers, so that they can become intelligent drivers for cloud native applications. So Yugabyte has two types of drivers that we provide. So one is based for our YSQL API, which uses Spring Data JPA, so that it has the JPA ORM support. Underneath, it can work with Postgres driver. Since we already said YugabyteDB is PostgreSQL compliant, you can very well go ahead and use Postgres driver. However, if you use the Postgres driver, probably you will need to have a load balancer in front of your YugabyteDB cluster, so that the application need not maintain the list of where the servers are running, right? Otherwise, it will be very complicated for the application to maintain that logic. That's why people kind of use load balancers. So in order for us to eliminate that need of having a load balancer and having another moving component, we went ahead and built a cluster-aware driver or a cluster-aware Postgres driver, which kind of brings in the topology awareness, which was like a commonplace to NoSQL database. NoSQL clients already knew how to access like the entire cluster, right? Like Cassandra's of the world, like DataSite Cassandra driver already knew how to do it. So we kind of brought all those features into Yugabyte JDBC driver, so that the JDBC clients are cluster and topology aware, because they know where the data is running, and they will know where the actual data is sitting, like which shard where the data is sitting. And we have other things like follower reads for lower latency, so that it can go and copy the local data copy, so that it doesn't go to a region that is not local. And also we have tunable read consistencies. All these things we have brought trying to bring into JDBC world. And also we have partition awareness, which means whenever we fire a query, YugabyteDB knows where the clients actually know where the data is actually sitting, so that it can go and directly run the query against the data there, so that it avoids a bunch of in-cluster rerouting, which kind of increases, which kind of reduces the latency and kind of supports the sub-millisecond response type that Yugabyte provides. In order to implement a Spring microservice with Yugabyte, we need only like just 5 simple steps. So I'll walk you through the code, how we have implemented both the APIs, like the YSQL API and the YSQL API. YSQL API. So the main things that we had to take care in a Spring Boot app is getting the right dependency. We had to have the right driver in the POM. And next thing, as soon as we have the Spring Data project on the class path, it automatically figures out to create the data source. And we have to add a bunch of annotations on your domain model to bring down the repository support. That's all it takes. Like within 3-4 steps, we can quickly implement the Spring microservice. So let me quickly, okay, before I go there, I see there is a question here. Is it not unexpected that checkout is not as well? I would have used only for product Sergio, it's actually right. So we have the product microservice also, the checkout microservice needs to be made SQL. Like when we deployed or when we designed this application, we had not thought about using SQL for checkout. That's why we went with SQL. Now we have more capabilities in Yugabyte to use SQL. Probably in the next iteration, we'll go ahead and change that checkout microservice to use a SQL-based design. Cool. Let me quickly go to my workspace. I just wanted to quickly show you 2 microservices. One is the product microservice, which is actually using the CQL aspect. So if I quickly go to the POM file, so if you see, as I said, we are Cassandra compliant. We are bringing down the same Cassandra, Spring Data Cassandra project. It's just that we are removing the data stack Cassandra driver core and using the Yugabyte driver. So Yugabyte driver kind of brings in all the shard awareness, topology awareness, and the distributed transaction that we support for all those features in our driver. So this is all it takes for an app developer to get started with YugabyteDB. And apart from that, if you see our the next thing as an app developer, what you will do is you will just see the domain, right? So for us, since it was product information that we were retrieving, so we have a product metadata, which is directly maps to products table. And we have a primary key assignment where the ASIN is a unique ID for each product. So in order to implement CRUD operations or in order to query this data, all we have to do is generate an interface called inventory repository. This is all it takes. Like my entire application, whatever we did in order to create the DAO for it. All I have to do is like just implement this repository. So to implement this repository, all I have to do is get the dependency. Within just 3 steps, I can quickly get started with implementing a microservice against YugabyteDB using Spring Data. That's the power that Spring Data and Spring Boot brings to the picture. And the YugabyteDB driver kind of brings in the cloud native features to the product. I see another question from Sergio. Sergio, that's part of my next slides. Yes, we do support Reactive. When we implemented this, this microservice, we weren't thinking about making everything reactive. Now we are thinking of making the entire webflow. It involves a slightly bigger refactoring. That's why we haven't gotten there yet. Like there's like a bunch of examples I'm going to walk you through next. Perfect. This is on the YSQL part. And similarly, on the cart microservice, I have 2 iterations of cart microservice, which is using the SQL API of Yugabyte. So if you see here, right now, I'm using Spring Data JPA because we want to use JPA as our ORM provider because it's widely used in the market, JPA and Hibernate, right? I'm using Hibernate, and also we are using Postgres. So in this microservice, since I'm using a Postgres driver, this is not data aware, or it's not cluster aware. It doesn't know the entire topology of our cluster. So that's why it connects to one Yugabyte T server, and it just communicates with that T server only. So there will be a lot of in-cluster rerouting that has to happen when you are using the Postgres SQL driver. So for that reason, we have another version of our microservice, like the V2 version, where we are using YugabyteDB JDBC provider. So if you see here, it is the JDBC driver that Yugabyte provides. In order to use this provider, all we have to do is we have to bring in our own data aware source. So if I go to my Java applications and my config, if you see here, Yugabyte data aware source, all I'm doing is I'm creating a data source, which is cluster aware data source driver. So this is the only change you have to do in order to implement your microservice so that it becomes an intelligent client like NoSQL clients. So internally, we have taken care of how the connection pooling works. Right now, we have a limit of creating how many connections gets created to all T servers in the cluster. All those things are configurable. And similarly, all we are doing for shopping cart is we are creating a CRUD-based repository, and all the transactional support that Spring Data provides will still carry forward with the Postgres driver that we are using. So if you see a bunch of updates that we are doing, everything is transactional. All we have to do is have a bunch of annotations, and Spring takes care of writing the boilerplate code behind the scene. So this, with a bunch of very straightforward annotations, we can quickly build our business logic as well. Okay, let me get back. Okay, this is what I was talking about in YSQL. It's just 4 things. Like all you have to do as an app developer, just make these changes your existing app, which is not let's say which is not using Yugabyte. In order for you to bootstrap that with Yugabyte, all you need to do is 4 steps. That's it. Okay, and we do have reactive support for YugabyteDB. On the SQL front, we integrate with the Spring Data Reactive driver that for Apache Cassandra. Like we can quickly show you a reactive-based CRUD repository, how it actually works. On the SQL piece, for YSQL, we are going to integrate with R2DBC Postgres driver. So currently, we have seen the basic compatibility with R2DBC Postgres driver. However, some of the things that Postgres driver currently doesn't support in R2DBC is similar things, right? It's not cluster aware, it doesn't know where the data sits, it's not distributed transaction aware, things like that. So we are coming up with a design document and coming up with a roadmap how we can start contributing to R2DBC Postgres driver and make it distributed SQL aware. I see another question from Sergio there. So R2DBC is not single threaded. So R2DBC is based on reactive streams concept. So if you understand how reactive streams work, it kind of utilizes all the available cores, all the available CPUs on your machine, right? So it is, it's basically works on the producer and the consumer and number of threads each have and a back pressure. So that's what R2DBC driver is based on. In order to, okay, let me quickly walk you through another code base, which walks you through the reactive support that we have. So I'll share it with you folks, like all these Git repos, which gives you a getting started sample for blocking and unblocking drivers. So in this, we are using the Cassandra's. If you see the dependency, this is the only dependency we need. We need to bring down the Spring Data Cassandra Reactive project. What this project provides us is, if I go, all I have to do changes like my repository, right? Like if you go and see my repository, in my repository, all I'm saying is I need to have a reactive Cassandra repository, which actually provides a non-blocking way of accessing Cassandra, the data that sits in Yugabyte using Cassandra APIs. So another thing, if I go to my controller, see how I'm using my CRUD, if you quickly see here, all I'm doing is I'm doing in a reactive fashion where none of my requests will wait for this database call to complete, because I'm already saying I'm going to return mono. Mono is nothing but mono is nothing but one of the primitives of reactive streams, where it returns a 0 or 1 in a future state. So with just these two simple changes, you can quickly change your microservices into a completely reactive stack. So one thing with the reactive stack is, in order to have full advantages of reactive stack, your entire stack, including your database, needs to be reactive. If your database is making you block your calls, very quickly all your producers will be like swarmed out of the resources, and there will be a lot of back pressure, and ultimately it will use all the resources, and your response times kind of goes down the hill. It's better in that case you just go with the regular blocking way of doing stuff. So in order to have a complete use of non-blocking way, your entire stack needs to be reactive. So, and also on the reactive front, we are currently on the design phase for R2DBC. If you folks have any feedback or ideas and things like that, we are very happy to hear from you. You can open up a support ticket, a Jira or a GitHub issue on our side, or you can come and talk to us on Slack. We'll be very happy to talk to you folks on that front. Not sure how much time do I have. Okay, cool. I think I have 5 more minutes. I can quickly cover this. So quickly moving on to the next slide. This is like one of the important things that we need to have as we move from traditional SQL backends to modern SQL databases like distributed SQL. So we need to have a way to eliminate load balancers, right? So without load balancers in the middle, we kind of have another indirection, and we have to maintain load balancer, and additional complexities are involved. So here's the thing, right? Like when we move towards a microservices architecture, obviously there's going to be a demand and for database scalability. So the first thing, like there is going to be a connection pool exhaustion. Like say if all your microservices are hitting your single monolithic database, like a single instance database, obviously like as you break down the apps, there will be more microservices, and database connections are super expensive. And it's compounded by, obviously it is kind of compounded by having a large number of applications connecting to the same database. So as and when more resources are being used in the database, it kind of deteriorates the performance, right? The query response time starts to go down, your CPU usage goes through the roof. Like you're hitting 90% of CPU utilization, but your latencies are going up. And in a situation like we are currently, where all the e-commerce applications or all the large internet scale applications are taking traffic by 2x, 3x, 5x, in such situations, there is going to be a lot of load on your database. Obviously, one way to kind of avoid having your database completely go down is to do query limiting, right? So you kind of move to a microservices architecture. However, you're still stuck with a monolithic database. Like ultimately, your scalability ends there. So traditionally, obviously, it's been thought out, and people have kind of scaled this. Like people have usually used what is called as a read replica, where you have a master node asynchronously replicating data to replicas so that they are in sync, right? So when you use read replicas for scaling your reads, there is one thing that you have to do. Either you have to make your client maintain list of all the servers where they are running. Like if a server goes down, comes back in, those things happens a lot when you move to a cloud native platform like Kubernetes. You never know where the pod gets reassigned. So you had to have those clients kind of maintain on the list. So in order to simplify business logic in the clients, people just go and use a load balancer. So load balancer, as we talked about it again, it kind of brings in additional complexity to the architecture, and it's another layer that you have to maintain and constantly monitor and things like that. And to scale writes, there's only one way to scale writes in a read replica. Like all we can do is in a read replica, only masters can take write, right? So you can only scale the database vertically, which means you are going to use like beefier machines, which like X1s and I1s in AWS, which are like super expensive. Obviously, they also have like a ceiling that you can do. Like write, most of the times writes are the ones that get hit because of using read replicas and a single master. So for that reason, we are thinking of coming up with, or we are working towards coming up with the cluster-aware JDBC driver. In this current incarnation, what this JDBC driver can do is it can automatically discover where the nodes are running without the needing of a load balancer. And also it provides a seamless way for the clients to get notified whether the server came back, or whether when you're scaling, it can automatically make connections to available servers and do a single hop fetch, which means you don't have to have an indirection after going into the cluster. It knows where the actual data shard sits, and your client can actually go and read the data from there. So this kind of very suitable for modern cloud native platforms like Kubernetes also. As I said, pods can go back up, come down, things like that. If you have an automatic way of figuring out the state of the cluster, it will be super useful for your cloud native applications. Now to quickly demonstrate this, I wanted to run an exercise here where I'm gonna show you 3 screens. One screen where I'm gonna expand my Yugastore instance. So right now I have let's just say 3 clusters, or 3. If I go to my pods, I have 3 T servers. That is where the actual data is sitting. So I'm gonna increase the T servers from 3 to 4. Before I do that, for capacity purposes, let me kill my other server. Like if you see, like it quickly, the other server also came up. For now, I'm gonna just delete it so that I have enough data so that I can scale my other cluster. Okay, perfect. What this does behind the scene is we are deploying a stateful set on Kubernetes. It's gonna just go and delete that stateful set. So even in our Yugastore instance, when I go ahead and edit my universe to scale it, all it takes, all it takes is to increase the number of pods. Like from, let's say we had 3, I'm gonna do it to 4. And it also increases the where the actual pods gets assigned. So right now I'm using a single availability zone. That's why all the pods gets assigned to a single availability zone. Before actually I go ahead and save, I'll do a couple of other things. Let me go ahead and watch the pod creation, like pod coming up. And for the namespace, right now, if you see, I only have 3 T servers, which are the actual data nodes. Then the other thing is my V2 version of the card microservice, which actually has the data aware client. I'm gonna tail its logs so that we can see whenever a new node joins. So this automatically discovers the node coming in. Okay, I have 2 containers, so I'm gonna get the logs of that container. Okay, perfect. Now let me go ahead and increase this from 3 to 4. Okay, let's just say save. Okay, what happens now is behind the scene, the Yugabyte, our platform goes and updates the stateful set definition, and it goes and provisions a new pod. So if you see here, there is a new pod that is coming in. So once the pod gets initializes and it gets bootstrapped, so this app needs to pick up the new pod coming in, or the new T server joining the cluster. It's going to take a few seconds for it to recognize it. So it happens in, I think we have like 10 or 20 seconds where the cluster state refreshes. Let's just wait for that. Meantime, I see there's like a couple of questions here. Let me quickly check to be sure how it works underlying driver, because where there is single thread. Okay. Sergio, I'll on the top of my head, I'm not sure if it's single threaded or not. I mean, my understanding of Reactive and my understanding of talking to the Reactive engineers when I was at Pivotal. So the way the web flux itself works, the web flux is the actual client. The web flux is the web controller reactive API, right? The web controller reactive API actually is not single threaded. So it is multi-threaded. It is actually uses all the available CPUs. I mean, one-on-one mapping, like it only creates those many threads. And maybe I can give you more explanation offline. I can reach out to you. If you can come to our, join our Slack, or if you're already on Slack, we can take it offline on our Slack. Before I address the next question, I quickly wanted to show one thing here. Like if you see here, the new host that came in, that was actually recognized by this application without making any code changes, or without you replacing that app or restarting the app or things like that. This is like the power of bringing NoSQL cluster awareness to JDBC clients. So this is going to be very powerful, as in when we move all the applications to start using distributed SQL databases. Okay, let me see what quickly, what other slides I quickly have. All I had was, I just wanted to round it up. The advantage of using a cloud native database in microservices architecture, right? Like, as you had seen, the smart drivers, the reactive drivers, the asset transactions, and having the ability for developers to create their instance very quickly on a modern cloud native platform like Kubernetes. makes it super advantageous for app developers to quickly start prototyping their applications. So that's why we think it's time for us to start thinking about modernizing our backend systems as well. Another thing that I just quickly wanted to talk about is the R2DBC Postgres driver. So R2DBC Postgres driver is the next active investment that we are doing. So we are gonna, in the next quarter, start working towards R2DBC Postgres driver, which is distributed SQL aware. So where we want to work, if you have seen the R2DBC spec, it kind of lists top 6-7 APIs which needs to be implemented by any Postgres driver, any database driver. Of that, of particular importance for us is the connection API as well as the transaction API, because that's where we can bring in changes needed for distributed SQL databases. Okay, any other questions